clouds can have both a cooling and a warming effect on the planet. But now let's talk about individual clouds and how they can affect the temperature. And let's start with the cirrus clouds. So the cirrus clouds, again, are very high clouds. You can see the picture on the top left, these wispy clouds. And you can actually see even in this image that we can see the blue sky through the clouds, which means that the sunlight coming into the planet can actually pass through these cirrus clouds fairly easily. They're fairly thin physically. They're made up of ice crystals, which are fairly large. So the sunlight can actually go through these clouds, but a large amount of the heat given off by the Earth gets trapped by these clouds. These are actually very efficient blankets to warm the planet. In the cartoon on the right, we can see that the sunlight, the red arrows coming in, can go through. They may change their direction, but most of them go through. We do have some reflection, does have a small albedo, but the heat, which is given off the yellow arrows from the surface, most of it gets trapped in. Some of it, again, will be re-emitted by the cold clouds above it. But when we look at the difference between these two, we basically see that overall the warming effect is much larger than the cooling effect. If we look at some of the numbers, for thin cirrus clouds, the albedo is about 10%, 0.1 is 10%. If we look at the absorption of the infrared radiation, about 50% of the radiation making it all the way up to the cirrus clouds will be trapped in by the cirrus clouds. But as they get thicker, we can see that the trapping in of the infrared radiation from the surface can reach up to 90%, while the albedo may only get up to maybe 42%. And so the albedo increases much slower for the cirrus clouds than the effect of the greenhouse and the trapping in of the heat. So we spoke about before that there are two forcings. There's a cloud greenhouse forcing and there's a cloud albedo forcing. For cirrus clouds, the cloud greenhouse forcing is much greater than the albedo forcing, and therefore when we put these two together, cirrus clouds tend to warm the Earth. So if we have more cirrus clouds in the future because of climate change, we're going to have more warming. If we have less cirrus clouds in the future, we're going to have less of a warming, and maybe even it will help cool the planet. We don't know which way it's going to go in the future, but cirrus clouds, if we change cirrus clouds, it has quite a dramatic effect on the temperature of the Earth. And if we could look in a little bit more detail, you can see here that if we change the optical properties of the cloud, we call this the optical thickness, but you can think of this either as the physical thickness of the cirrus clouds or the amount of water or the amount of ice in these clouds. As we get more and more, so 0 means we have no cloud. As we have more and more of the cirrus clouds, we can see both the solar albedo effect increases, and the y-axis is given in percentage, again from 0 to 100%. So by the time we get to an optical thickness of 10, a very thick cirrus cloud, we have still an albedo of maybe 40%, which means 60% manages to go through those clouds and come to the Earth. The red curve is for the emission of the infrared, or what we call the thermal effect or the thermal blackness, how much as it gets absorbed of the heat given off by the Earth. And we see this increases very rapidly as the cloud gets thicker and saturates at about 100% by the time we get to an optical thickness of around 6. And so the thermal effect is always much stronger for the cirrus clouds than the solar effect. So if we put these two together and look at how this theoretical cloud would impact the Earth's temperature, so the y-axis here is now changes in temperature from, say, a 0 value, which is a reference value, for no clouds, and now we add more and more cirrus clouds, they become thicker and thicker. We see the thermal effect on the top. The solar effect always has a cooling, so the blue curve shows that we have negative numbers, so that it's a cooling. The red curve has a positive effect, and the combination of them we see in the middle in yellow, which is the effect of cirrus clouds at a specific altitude. I didn't mention that. This is for a cloud at 8 kilometers above the ground. And what we see is that as the clouds get thicker, we see that we have more of a warming effect. This reaches some saturation around about 3 degrees. And then as the cloud gets thicker and thicker, the albedo, the reflection, starts to have more of an effect. And we start to see that now the warming effect decreases, and eventually, with very thick cirrus clouds, can actually go below the zero line for temperature and can actually have a cooling. So if we have very thick cirrus clouds, and this occurs on the anvils of thunderstorms. So when you have a thunderstorm developing and goes up to 18 kilometers, the outflow is basically ice crystals or cirrus clouds. And these can be quite thick. So they'll actually reflect a lot of sunlight. They'll also trap in a lot of heat, but overall they can have a cooling effect. But most of the cirrus, the fair weather cirrus, basically the wispy clouds we see in the sky, are of optical thickness maybe around about 2 or even less, and therefore they always have a warming effect. Now we can also play this game with how, if we change the cloud fraction, how much cirrus cloud we have on the globe, or the thickness of the cloud, and how that'll affect the temperature on the planet. So again, this is for a cloud at 8 kilometers, a cirrus cloud. These are, again, theoretical calculations. And we see if we have no clouds, then we have no change in temperature. But as we go to higher fraction, the x-axis is the percentage of the planet covered by cirrus clouds, so 10%, 20%, up to 50%. If we follow one of these lines, and each line represents another optical thickness, another thickness of the cloud, we see that it doesn't matter which line we follow. As we have more coverage, the Earth is covered with more and more area of cirrus clouds, we see that we have warmer and warmer temperatures. We go up these lines. And if we also just take at this point 1, if we take the same coverage, so only 10% of the planet is covered by clouds, but we increase the optical thickness, which is going from one line to the next, we also see we can warm the climate. So both changing the properties of cirrus clouds, making them more thicker, but also changing the coverage, both of these will result in an additional global warming. I also mentioned that we were looking at 8-kilometer clouds, but if we change the altitude of the clouds, we can also impact the climate of the Earth. And that's because the amount of energy which is absorbed from the Earth, that infrared radiation, the long-wave radiation, the amount that gets absorbed and re-emitted depends on the temperature or the altitude of those cirrus clouds. The higher the cirrus clouds, the larger the warming effect on the climate. When those cirrus clouds are close down to the surface, we don't have a very large warming effect, and we can see that the zero line gets crossed a lot sooner than for clouds which are higher up. So when we have high clouds, like at 8 kilometers, for basically any cirrus clouds, it will have a warming effect. But if these cirrus clouds in the polar regions, ice clouds around about 2 kilometers altitude, as soon as we increase them by optical thickness more than, say, 1, we start to have a cooling effect. So the height of the altitude of the clouds is also important, and this too is something people are studying for climate change. How will, even if we don't change anything of the cloud properties, the cloud coverage, we just change their vertical distribution. If we make the clouds higher, they'll also have a warming effect on the climate. So it's very complicated how clouds are going to change in the future, but they can change in many ways which can impact the temperature of the Earth and the climate, sometimes amplifying it, and maybe sometimes they can actually work to cool the climate. So where are these high clouds, these cirrus clouds? Here you can see a composition of many years of satellite data, again showing the percentage coverage in certain areas of the planet, and the blue areas are where we have the most cirrus clouds. So these cirrus clouds are often related to areas where we have lots of thunderstorms, these cumulonimbus clouds in the tropical regions over Africa, over South America, over Western Pacific and Indonesia. Less so when we go to the oceans, and less so when we go to the higher latitudes. So the areas where we can see the significant warming from the cirrus clouds is actually in the tropics, where it's warm to start off with. On the one hand, we said we have a cooling effect because of the albedo, but we also have this blanket, this greenhouse effect. And so when we have changes in the cirrus clouds in the tropics, this can have a major impact on the temperature in the tropics, which can then spread around the planet.